So, good morning. Welcome to the next lecture on modulation. In last lecture we started with complex baseband to passband representation, and we developed an important picture of that relationship which is here. So, what we have said is we have a complex baseband signal which is ST. You multiply this with a rotating complex exponential, take the real part and you get a passband signal, a real passband signal, and you can go from passband signal to the complex baseband signal by passing this passband signal through a Hilbert filter and then again multiplying with the suitable rotating complex exponential, and you get back complex baseband signal. Okay. So, this is to help us understand analytically what goes on, and in terms of reality these things are implemented something like this. So, you have SCT, which is the real part of this complex baseband signal, multiply this with cos omega CT, multiply SST with sin omega CT, add these two things to get SPT, and then we can also go back from SPT to SCT and SST by having again the multiplication with cos and sines and passing them through low pass filter. And then you can accept or take this SCT and SST, and a baseband processor can process these signals. Today we will like to carry forward this idea of establishing equivalence between complex baseband and passband signal, and we like to first study three important properties. So, three important properties that we will study and prove in today's lecture are this. So, first property that we will prove is SC cos omega CT, which is also known as I component, and SS sin omega CT, which is the Q component, are orthogonal to each other. Remember that sometimes I write SC and sometimes I write SCT. So, SC is a function of time, right, and sometimes for typographical reasons I simply write this as SC, it is more convenient, right. Your equation does not become cluttered with this T. So, whenever you see SC you should understand that this is a function of time, right. We do not have to have this T at all times. Okay. So, SC is nothing but SCT and SS is SST. Okay. So, that is the first property that we have to prove, that I and Q components are orthogonal to each other. The second property that we have to prove is inner product of SP with XP. SP and XP are the passband signals, P represents passband signals, and again I do not have T in here, is same as the real part of inner product of S and X. S and X are the complex baseband equivalent of these passband signals. So, this is the second property that we have to prove, that inner product of passband signals is same as the real part of inner product of their equivalent complex baseband signals. S and X are the complex baseband signals of SP and XP respectively. The third property that we have to prove is energy of SPT passband signal is same as energy of baseband signal. Okay. And this will follow because of the normalization factor that we used the normalization factor of root 2, and this is to make the energy of the passband signal same as the energy of its equivalent complex baseband signal. And later when we do detection, we would see that the performance of the detector depends upon the energy of the signals, right. And if the energy of the passband signal is same as the energy of its complex baseband signal, then we do not lose anything, right. So, whether you detect ST or SPT, it does not lead to any deterioration in the performance. So, these are the three important properties that we will first derive, and then we will move to other things. So, let us start with the property number 1. So, we have to prove SC cos omega CT and SS sin omega CT are orthogonal. And to prove this, what we need to do is that their inner product is 0. That is what you require to prove the orthogonality between the two signals. So, we take their inner product, which is SC cos omega CT, SS sin omega CT dt is, we want to prove that this is 0. Well, what you can also do is, so I have omitted t, we can put it t here. So, we have to prove that this inner product is 0. Okay. Now SCT cos omega CT and SST sin omega CT, everything is real, right. That is why in this inner product there is no conjugate or anything, everything we have assumed to be real. Now, if you want to prove this to be 0, a more instructive way to do this is by proving this is 0. What is this XCF? XCF, we have defined it to be Fourier transform of SCT cos omega CT, and XSF we have defined to be the Fourier transform of this. So, we have considered two signals. So, let us say that this, let us treat it as xt and yt. So, what we are saying is xt has a Fourier transform XCF, yt has a Fourier transform XSF, and so from Parsible's theorem we can write this. Remember Parsible's theorem, what is Parsible's theorem? Let me rewrite Parsible's theorem for you. Parsible's theorem says that xt yt conjugate dt is xf yf conjugate df. When you run down its integration from minus infinity to plus infinity, these two quantities are same. So, this is the inner product of the two signals, and this inner product, this is also the inner product in the two signals spectrum, right. So, whether you take the inner product of the signals or you take the inner product of the spectrum of the signals, inner product is same, inner product is preserved when you move, when you go from time domain signal to spectrum. Now, because my yt is real, so I can say xt yt dt should be same as minus infinity to infinity xf yf conjugate df, and this is exactly what we have written there. So, this we have considered is to be xt, this we have considered to be yt, we wanted to prove that this is 0. So, we can prove this is 0 by saying that XCF into XSF conjugate df is 0 from Parsible's theorem. Okay. So, now let us see what is this XCF. There is also a one line proof for this, but why we are doing such a lengthy proof is because this proof is more instructive, right. You learn more when I carry out this lengthy proof. So, XCF, if you look at this, it is nothing but, so let us define SCF. Let me also define that SCT, let us say that this has a Fourier transform SCF. So, SCT into cos omega CT would have a Fourier transform SCF minus FC plus SCF plus FC by 2. Okay. So, this is from Signals and Systems course, very basic stuff, and I assume that you know this. So, XCF would then be half SCF minus FC plus SCF plus FC by 2. Similarly, we can say that XSF is 2J SSF minus FC minus SSF plus FC, okay, because instead of cos omega ct it has sin omega ct, right. So, based on this we can get XSF as this. Now, let us try to take this with the conjugation. What you would end up with is XCF into XSF conjugate df would be nothing but minus 1 by 4j. I am not explaining the constants because they are not so important, right, because we have to prove anyway it is 0, right. So, the constants values are not so important as such. So, what we would have is SC f minus FC plus SC f plus FC multiplied by SS f minus FC minus SS f plus FC, and these things would come with conjugation. We have to see what this integration is, and what I have done is nothing, I have just replaced the values of XCF and XSF. If you look at this now, the big idea comes that if you look at this thing, let us worry about what is the multiplication of this with this. So, let us see what is SCF minus FC into SS conjugate F plus FC. Now, if you look at this, and this is a big idea because most of the time we would be using this idea, is this is the spectrum which is centered around FC. So, if I look at this, this would be some spectrum which is centered around FC, and this is a some spectrum which is centered around minus FC, right. So, one is this part of the spectrum is centered around minus FC, this part of the spectrum is centered around FC. When I multiply these two things, there is no overlap, and hence this multiplication gives us 0. Okay. So, this times this would give me 0. Similarly, if I multiply this with this, it also will give me 0. So, in the end I can reduce this integration by having minus 1 by 4j. What you would end up with is, let us try to see, yeah. So, first part you would have SC f minus FC times SS f minus FC conjugate, let me write it as 2 integration minus 1 by 4j minus infinity to infinity. Let us see what we have is, we would have SC f plus FC into SS conjugate f plus FC df. Let me check the signs. So, this would come with a positive sign. Okay. So, this is what we would have finally. Now, let us look at this expression. Let me use different pen and let us see what SC f plus FC into SS conjugate f plus FC df is. So, to understand this, let us change the integration variable. So, let me define f plus FC is some f naught minus FC. okay, the change in variables. So, I can write this integration, let me write this, what we would have is S c. So, f plus f c can be replaced by f naught minus f c. So, we would have S s conjugate f naught minus f c, d f is nothing but d f naught, and because f was varying from minus infinity to plus infinity, f naught will also vary from minus infinity to plus infinity. Okay. So, we have this is same as this, and this in fact is nothing but it is same as okay, just replacing f naught by f. So, this quantity what we had is same as this quantity, okay, and they comes with the opposite sign. So, this integration boils down to 0. So, hence we have proved that the inner product of I and q components is 0, and this is an interesting fact. Let us try to prove the second point, or let us try to see the second point, the inner product of the passband signals and the inner product of the baseband signals. So, let us try to look at the second point. We talk about the inner product of passband and complex baseband signals. So, let us see what it is. So, let us try to think about taking an inner product of SP and XP, and SP and XP are the passband signals. I am not writing the T here because I know that you can assume that there is a T, and it is always inconvenient to write every time this T. So, for that simple reason, for this typographical reason only, I have omitted T. There is no technical or deep reason why I have omitted T. Okay, it is just for writing convenience. So, this inner product if you see is, then I write it in full, that means I want to take the inner product of this quantity with the passband XP So, I have to take the inner product of this quantity with this quantity. So, x c and x s, as you would guess, these are the cosine and sine parts of the passband signal x p. Okay. Now, because inner product is a bilinear operation, I can take inner product of this term with this term and this term with this term and so on and so forth, right. So, let us start. So, first thing that we can do for convenience is to pull out these root 2's and make it 2. So, I have 2, then let us see. So, first I take the inner product of this with this. So, I have S c cos omega c t, inner product with x c cos omega c t. Then I need to take the inner product of this with this, and this is 0 because what I am doing is I am taking the inner product of I with the q component, and we have already derived these I and q components are orthogonal, and hence their inner product is 0, right. So, this gives us 0, and so I do not do it. Similarly, the inner product of sin omega c t with cos omega c t is also 0. Okay. So, what you end up with is simply you need to just multiply this term with this term and this term with this term, and 2 is already been pulled out. So, I can simply write that this is as S sin omega c t's inner product with excess sin omega c t. Okay. All right. Now, let us see what is the inner product of SC cos omega CT with XC cos omega CT, and as everything is real, I do not unnecessarily put a conjugate. Okay. Now, this is very simply SC XC 1 plus cos 2 omega CT by 2 dt, and this is minus infinity to infinity SC XC by 2 dt plus half minus infinity to infinity SC XC cos 2 omega CT dt. Now, you have to very quickly judge that this part should be 0. Why is this 0? Because SC and XC are the baseband components. Baseband components means their frequency spectrum is centered around DC. This is a component whose frequency spectrum lies at around 2 omega c, right. So, there is no overlap in the spectrum of these two signals, and if you invoke Parsifal's theorem and if you have done the proof of the property 1, it is should be very clear to you that this integration should go to 0. If it is not clear, I would urge you to look at the proof of the property 1. Okay. The idea is very simple. Baseband signals, this is a passband signal at 2 omega c, no overlap in the spectrum, and hence this integration would turn out to be 0. What you then end up with is this quantity, and what is this? This quantity is nothing but it is half times inner product of SC with XC. Okay. So, what I can write is using this idea that inner product of SC cos omega CT and XC cos omega CT is nothing but it is half times inner product of SC with XC, and there is already 2 here. So, you can multiply this 2 with half, and what you can simplify is it to is, so inner product of SP XP, I said it is 2 times the inner product of SC cos omega CT with XC cos omega CT plus inner product of SS sin omega CT and XS sin omega CT, and this is SC XC inner product and SS XS inner product. So, this relationship establishes the link between how can you think about the inner product of 2 passband signals by just carrying out this inner product operation in baseband domain, because all processing happens in the baseband domain. So, if you want to take the inner product of the 2 passband signals, just do it in baseband, right. Extract the sine and cosine part of SP the way we have done before, and extract the sine and cosine part of XP the way we have done before, and then take the inner product of these parts in this way. Okay. Now, let us see what is the inner product of ST with XT. So, what is ST and XT? They are not passband signals, but they are the complex baseband representation of the passband signals. Remember, this is the notation that we are following. SPT is a passband signal, ST is a complex baseband representation of the passband signal. So, now we are interested in taking the inner product of ST with XT, and let us see what it is. So, again this can be written as SC plus J times SS. So, again I have omitted the T for typographical reasons only, and XT is XC plus J XS, the complex signal. Now, taking the inner product, again term by term we can take. So, this would give us SC with XC inner product, this then we have to multiply, let us say, with this, the J will come with a minus sign, SC excess. To multiply this with this, j will come with positive. Remember the bilinear properties of inner product. If you have forgotten about them, just revise it, it is simple. Then I have to multiply this term with this term, I get minus and this j comes with a conjugate. So, there would be a plus SS and XS. So, I can write this as SC XC's plus SS XS plus j times SS XC minus SC XS. Okay. The most interesting thing to see that if I take the real part of this quantity, what I end up with is this, and this quantity, as I have seen, is nothing but it is the inner product of SP with XP. Okay. And hence, now I have a relationship between the inner product of passband signals and its complex baseband representation. So, there is a big idea that inner product of SP with XP is nothing but it is the real part of the inner product of ST and XT. Okay. This is the relationship between the inner product of passband and inner product of baseband signals. Let us prove property number 3rd, and this property is about energy of passband and baseband signals. Baseband, I mean complex baseband representation of the corresponding passband signal. So, complex baseband. Okay. Now, what is the energy, let us say, of SPT of the passband signal? Energy is nothing but you need to take the inner product of the signal with itself, right. So, this is SPT with SPT, you take the inner product of the signal with itself, you get the energy of the signal, and this is nothing but it is norm of SPT square, right. This is typically the representation. This we have already seen that when you take the inner product of the signal with itself, what you get is the norm square of the signal, right. What is the energy of ST? It is again the inner product of ST with ST, and this is nothing but again the norm of ST square. Very simple, straightforward. Now, the question is, what is the relationship between this quantity and this quantity? Can we relate it? Yes, we can relate, because we have already seen that inner product of SPT with SPT is nothing but it is the real part of inner product of ST with ST, is not it, from the previous relationship. And this quantity is nothing but SPT square, which is the real part of norm of ST whole square. And amazingly, norm is a real quantity, right, because norm denotes the length of a signal, and length is a real quantity. So, this is a real quantity anyway. So, taking the real part does not mean anything. So, I can simply write this as norm of ST square. So, this is the energy of SPT and this is the energy of ST. How did we get the energy of a passband signal same as the energy of the baseband signal? This is because of the normalization factor that we have used in our expression. So, we have used a normalization factor of √2. The reason why we wanted to do that is because we want to get the equivalence between the energy of a passband signal and the baseband signal, and that is why we have introduced that complexity. Certain books which do not use this normalization factor of √2, energy of passband signal will not be same as the energy of the baseband signal. Okay. In our case, this has turned out to be true because of that normalization factor. Okay. Let us now go and try to establish frequency relationships between passband and baseband signals. Let us try to see that what it is. And before we see this, let me ask you to have another look at the picture that we developed for relationship between ST and SPT. As I have said before, this picture is really useful picture. Let us look at this picture again. Okay. Using this picture, we can easily see what is the relationship between the spectrum of XT and SPT. So, let us do it. Okay. So, let me draw one by one again these blocks. So, let us start with ST, multiply it with root 2 e to the power j omega ct, take the real part, and what we get is SPT, this we know, right. So, let us see now what is the relationship between the spectrum of SP and spectrum of ST. So, let us assume that the spectrum of ST is SF. Let me call this quantity as SAT. What is the spectrum of SAT? Let me call this as SAF, and let me call this spectrum as SPF. Okay. So, what is the spectrum SAF? SAF would be nothing but, because SAT is ST multiplied by this quantity. So, spectrum of SAF would be simply root 2 times SF, and because ST is multiplied by rotating complex exponential, as the spectrum would just shift, right, and it would get positioned at around FC. From baseband it would go to passband. Okay. So, this is a spectrum SAF. Now, what is the relationship between ST and SAT? ST is real part of SAT, sorry, SPT, the passband. So, this passband signal is a real part of SAT. Okay. So, if I want to take a real part of a quantity, what should I do? The real part of a quantity is just the quantity, and you add to this quantity its conjugate divided by 2. Okay. When you add the conjugate, the imaginary part cancels out, and what you end up with is 2 times the real part, and that is why you have this addition divided by factor 2. Very straightforward kind of things that should be bread and butter for you once you have finished the course on signals and systems. Now, if I know this, the spectrum of SPT, which is SPF, should be half the spectrum of SAT. We have called this as SAF. Spectrum of SAT conjugate. Now, this is again trying to use the property from signals and systems. This spectrum of this signal would be SA minus F conjugate. Okay. So, you must have learned about conjugate symmetry and things like that, and this is the invoking and using the same idea. So, if you want to take the Fourier transform or the spectrum of SAT conjugate, this would be SA minus F conjugate. So, I would not prove this, I would simply use this, and from thus we can say SPF would be half SAF. What is SAF? We have already derived. So, there is a root 2 factor which I would take together. So, this would be SF minus FC, and then SA minus F conjugate. So, this would be S of minus f. So, f becomes minus f c, and this quantity comes with a conjugation. So, what we have then is 1 by root 2 times S f minus f c plus S conjugate minus f c. So, this relationship establishes the link between the spectrum of the passband signal and the spectrum of the complex baseband signal. Okay. Let us now try to do the things in the other way. So, let us try to see what is, how can we obtain the spectrum of complex baseband signal from the spectrum of the passband signal. So, I would use this picture that we have SPT, we pass it through Hilbert filter, and then I multiply this thing with root 2 e to the power minus j omega c t, and I get S t. Now, things are easy. So, this spectrum here, so if my spectrum here is SPF, the spectrum here is the positive part of this. So, I denote this with SPF plus. SPF plus means simply that this is SPF for f greater than 0, and this is 0 for f less than 0. Okay. So, it is just taking the positive part of the spectrum of SPF, and that is what the Hilbert filter does, it just kills the negative spectrum. So, the spectrum of ST, which I call SF, should be root 2 times S plus f. Now, because of this complex exponential, we have the spectrum of SPF shifted to minus Fc. So, this relationship links the spectrum of the passband signal and a baseband signal. So, let me write down both the equations together. So, the two equations together are these. So, this links the spectrum of the passband and baseband signals. Let us do one example about this, a simple example. So, let us say that I have a passband signal whose spectrum is this. This is f equals to 0. I have such a spectrum, and let us say that my minus Fc is here and plus Fc is here. Now, first of all, looking at this spectrum, we know that SPT must be a real signal. So, this is SPF. Why? Because we have seen that if my SPT is a real signal, then the magnitude of the spectrum should be symmetric, it should be even, and that is the case here, the magnitude of the spectrum is symmetric. So, this underlying signal should be a real signal, or it might be a real signal at least, right. So, that we get that clue from this picture. Now, to get the spectrum of SF, we can use the relationship. So, the one thing that we have to do is, first we have to kill the negative part, and then we can translate the positive part towards negative direction, because this is plus Fc. So, this should be shifted by minus Fc towards left. So, resultant spectrum would be something like this. So, this is the spectrum of SF. Now, if you look at this spectrum, you can notice two important things. Now, the magnitude spectrum is not even, it is not symmetric, and if the magnitude spectrum is not symmetric, we know that the underlying signal must be a complex signal, and that is the case. ST in general is a complex baseband signal, and the spectrum would not be symmetric around 0, and now we know that this is for analytical convenience. One thing that I would like to point out at this stage is, if suppose we want to define the bandwidth of SF, and suppose SF is given like this, right. So, I have some signal and whose spectrum is given like this. How do we define the bandwidth of such a signal? In case of the signals which are real, for example, their spectrum would be symmetric around DC, and we say that the bandwidth definition that we normally choose is the one sided bandwidth. So, meaning that if you want to talk about the bandwidth of this signal, this bandwidth would be one sided bandwidth, means the range of positive frequencies. And the idea that we have why we use this definition there is, anyway this is just a duplication of this part, it is symmetric. So, there is no extra information available in this component, and hence we take the bandwidth just to be the bandwidth of the positive part. In this case, what should be the bandwidth? Now, there are many definitions that exist in literature which define the bandwidth of such a signal. One idea is that you take the two sided bandwidth, let us say the two sided bandwidth is W, and then you divide this two sided bandwidth by 2, and you treat this as the bandwidth of this complex signal. That is one definition that exists in literature. However, according to me, the better definition of bandwidth for such signals is the complete two sided bandwidth. So, the definition that we like to use is the bandwidth of a complex signal is two sided bandwidth, and the idea is very simple. The idea is that this complex signal does not exist in reality, this is just an analytical signal, and this signal corresponds to a real passband signal, is not it. So, this signal actually corresponds to a passband signal which has the spectrum like this, and the bandwidth of this passband signal is the complete range of this triangle, and hence if you want to think about what is the bandwidth of this signal analytically, the more proper definition of the bandwidth would be two sided bandwidth. So, that because this two sided bandwidth corresponds to the bandwidth of the physical passband signal to which this complex baseband signal corresponds to, and hence we would use this as a definition of bandwidth of a complex baseband signal. Okay. So, we have developed some key ideas in this lecture. We have understood how to define the bandwidth of a complex baseband signal, we have understood how to take the inner product between a passband and a baseband signal, we have looked at the energy equivalence between passband and baseband signal, and we have also established the orthogonality between I and Q components, and we have established the relationships between the spectrums of passband and baseband signal. Now, what we would do is we would try to learn how to carry out certain passband operations in baseband. How to do this? We would learn about these things using some examples, so that whatever we have learned can be made use of. So, things that we would do now is we would try to see basically three important things. Suppose I want to implement a filter, or let us say passband filter in baseband. How can we do that using the ideas that we have established? So, this is the first thing that we will learn as an example, or trying to use things that we have learned. The second thing that we would see is, so there are certain effects which we will talk about, frequency offsets or phase offsets, which reduces the performance of our digital communication. system receiver or a system in general. So, we would try to see can we get rid of these effects by doing some processing in baseband, and we would see that. Third idea that we would like to develop is how can we think about this coherent receivers and non-coherent receivers in terms of the inner products and things like that that we have discussed, and how can we think about these receivers in baseband. So, with these 3 examples we would complete this discussion on this complex baseband and passband equivalence, and then onwards we would start with this spectral description of sources. So, these examples we will discuss in the next lecture. Thank you.